In this video, I'm going to go over linear and nonlinear regression, and I'm going to use data for vapor pressure and temperature, the relationship between pressure and temperature, and we're going to be doing it with water. So we're going to get data from this site called GitHub, and it's going to give us a bunch of data points for water vapor pressure compared to temperature, and we're going to use that data to create a model for linear and nonlinear regression. We will be basing all of our calculations off of the Antoine equation, which I'll talk about here in a minute. And so we're going to run the data through the Antoine equation. We'll have to manipulate it a little bit for the linear regression, and then we are going to get the constants. We will just find the values for the parameters that minimize the error in our models. We'll use a little bit of statistics and general calculations to figure out, to make the model fit. And we are going to bring it out really quick. Okay, so this is the Antoine equation. Basically, it is comparing our two variables here. This is the pressure and temperature. We will have our temperature in Kelvin and pressure in pascals, and the temperature is the independent variable and the pressure is the dependent variable. A, B, and C are all constants, so those are the parameters that we are going to try to solve for using matrix multiplication and our code. Just like a brief description of what the Antoine equation actually is. It's just a correlation between the vapor pressure and temperature of a pure substance. In this case, we're going to use water. So that's the Antoine equation, and that is what we're going to use for our calculations. And we're going to determine the constants for the equation, and we're going to use experimental data to do that. Next thing I'm going to talk about is just what is linear and nonlinear regression. Essentially, they're very similar. Linear just means it has the form of y equals mx plus b, or something similar to that, where you can graph it linearly and run linear regression on it. Nonlinear would be something like this, or some other form where we can't do linear regression, but we're going to be able to manipulate this equation so that we can fit it linearly and non-linearly. But essentially, both linear and nonlinear regression use one variable to predict another. Okay? So, and then we're going to do that graphically. So when we put our data through the Antoine equation and when we put it in our code, we're going to get something like this, where we will have a graph. Hope the computer can see this, and then we'll have all of our data points. It might look something like that. The rover will have temperature and a log of the pressure. And then when we get our model, we'll do something like that. Now we want to make sure our model is as good as it can be, because right now some of the points will lie on the line, but some of them will be a little bit further away. And we can even make these little squares. So this is the distance between the experimental data and the predicted data. So something like that, where you'll have all of these errors in our data. So what we want to do is we want to minimize that error, and in order to do that, we need to use something called sum squared error. So I'm going to erase this guy, and let's talk about sum squared error. So the sum squared error is essentially, it just measures the variation in the modeling error. And so we want to, in order to minimize that, we need to have a function, and we want to calculate the sum squared error, and then we'll minimize it. And it basically is just, we're going to add up all the deviations of the data, take the difference between the experimental and the model, and then square it, and use that to minimize the model parameters A, B, and C. So I'm going to write out the equation for it. That's my sum symbol, it's not very good. It's basically, it's just going to be from the initial data all the way up to however many data points there are, and then we're going to do it like this. The error is for the dependent variable, the pressure, so we're just going to be using the experimental pressure, that's what this I means, and we're subtracting what the model thinks it should be, this A minus B plus D. And then we're going to square the whole thing, and that will calculate our sum squared error. Once we have the sum squared error, then we can use the code in Python to extract our A, B, and C for the nonlinear regression. So we'll run this through, and we can define the variables, and then we'll have A of the nonlinear, and then we can separate it like that because we're going to minimize it, and then we can just make, for the nonlinear regression, we can make any guess that we want. We can figure out what we think will work best, but basically just guess and put different things for A, B, and C. For the linear regression, though, we want to be a little bit more accurate, and so we need to calculate the linear model for the Antoine equation, and then it will give us specific values for these parameters in our Python code. So let me erase really quick, and I'm going to show how we calculate linear regression so that we don't have to just guess what we think the parameters should be. I'll leave that actually up there, and that's fine too. Okay, so in order to transform this into a linear model, we need to use what's called a matrix. A matrix is essentially, I'll actually write. A matrix is just an array of numbers, and it's arranged columns. So what we're going to do is we're going to transform this into a linear format so that we can make a matrix for it and do matrix multiplication in our Python code. That way we can get specific values for A, B, and C. So what I'm going to do is just going to move some things around with this equation. I'm going to multiply both sides by C plus T. So we'll get the log of the pressure times C plus T plus and that's what we get. And then I'm going to keep the temperature times the log on this side, move the other log to the other side, and we're going to get temperature log of the vapor pressure equals if you want to be, not the other way around. Okay, so then, and this is kind of annoying because these are all just constants, so I'm just going to end up calling this something else. I'm going to call this D, so then we can write T log P equals Awesome. This we can run through matrix multiplication, and then we can do linear regression. And I'm just going to erase a little bit, that way we can draw out the matrix. I'll write it over here actually, make sure screen fits. Okay. Alright, so for our matrix multiplication, we're going to have our design matrix, which is going to be the temperature minus the log of the pressure, and then we're going to have our vector of unknowns. Actually, I'll just write it down. Use sky. These are our experimental values, so this is T1 minus P1, and it goes all the way down to however many data points we have. Vector of unknowns, which is our A, C, and D equals, and then these are going to be our Y values, which is the T1 log of P1, again, all the way down to T2, or Tn log of Pn. Just like that. Okay, I'll write out, this is the experimental, for the X values. This is design matrix. This is our vector of unknowns, and then this is our Y values. So what we want to do is we want to take the inverse of our design matrix so that it just turns into 1, so that way we just have the vector equals our Y values, but we can't take the inverse of this matrix because it's not an n by n matrix. So what we have to do is we have to multiply it by the transpose of the matrix, and transpose multiplied by the X. The transpose is just over here. Some of the key words. Transpose is just matrix flipped on the diagonal, so it's just switching the rows and the columns. And so then we can get the coefficients for the vector of unknowns once we run this matrix multiplication, which we'll ultimately end up doing in Python. We have to first multiply by the transpose of X to both sides. We take the inverse of both sides, and we end up with this is just our identity matrix. And that's just ones on the diagonal. So then we just have our formula for our vector of unknowns. I don't know why that's an L. Why are these L's? It's a great question, I don't know. So essentially the vector of unknowns equals the transpose of our design matrix multiplied by dependent or the Y values, and then we have the transpose times the design matrix, take the inverse of that, and that will give us our A, C, and D, which we can then use in our linear model. We're going to put it into Python on this system called Colaboratory, which I'll talk about in the computer video, but essentially we're just going to run all of these things in Python, and it will show us a plot of the linear and nonlinear regression for water vapor pressure compared to temperature using the Antoine equation. Okay, so now that we know what we want to put into our code in order to model our data, we're going to go ahead and just do that. So we're going to be using a site called Google Colaboratory. This is a product of Google Research. It's a development of Python that Google released, and it's entirely free for everyone to use, and so this is what we are going to use. I'm just going to go ahead and make a new notebook. Alright, awesome. And then we can just start putting things in. So the first thing we need to do is get our data. We're going to get our data from this site called GitHub. And this is our water vapor pressure data here. Okay, and we just want to use the raw CSV data file. So this is what we got. It's the temperature and the vapor pressure are separated by commas. So when we go to code and separate them out, we want to make sure we are aware of that. So we're just going to go ahead and copy this link. Go back over here, and then we're going to put the data in here. And I like to run things as I go just to make sure they work. Awesome. So we've got to go ahead, we've got the data in here. Now what we want to do is we're going to be using a site called NumPy, or it's an extension of Python, and it's especially used for scientific coding and syntax. So we're going to import NumPy as P. Oh, spelled import wrong. Okay. Awesome. So now let me just make sure I did all the syntax correctly. Awesome. Now we're going to go ahead. Oops. Okay, so now we're going to load in the data and separate the vapor pressure from the water. I'm just going to call it data equals numpy.load text, and it's water vapor pressure .csv, comma, delimiter is a comma. Let's see if that worked. NumPy has no oh. There we go. Alright, sometimes it takes some trial and error. And we can also make sure that our file is actually loaded over here. So that's what we got. So we loaded it correctly. And now we're going to separate. Awesome. Okay, so that's good. Now we can go ahead. So now let's go ahead and define our variables, the temperature and the pressure. Now that we have the data separated, I'm just going to do, let's just do simple T equals from the data. The temperature was in the first column, and Python syntax starts at 0, so we have 0 like that, and then pressure, just call it lowercase b, make it simple. And we want to do the log of the pressure, log base 10 of the data. It's going to be okay. Let's make sure we define those correctly. Awesome. Now let's make our graph. Fig equals make subplots. Rows. Okay. We're going to do a scatter plot. the temperature on the x-axis because it's the independent variable, and the pressure on the y-axis because it's the dependent variable, and we want it to be as markers because it's experimental data. Can't type apparently. And let's just call this one data. Okay, let's see if that works. Oh, it's because I can't type. Yay! Here's our data. So now that we have our graph, that makes sense. Just one more time. Awesome. Now we are going to start using the sum squared error to make our model for the nonlinear regression. In order to do that, we're going to need to use a site called SciPy Optimize. It's basically just used in Python for minimizing or maximizing functions and other nonlinear regression. So we're just going to import that up here. In order to use SciPy Optimize, import, and we want to minimize the data. We need to have a function first, so let's make our function here. We're going to define, I'm just going to call it sum squared error, and we have our vector of unknowns, which is just the a, b, and c. Awesome. And then let's do just a, b, c equals the vector. We want to return sum of, and then this is where we put in the Antoine equation that we solved for, or that we used to calculate the sum squared error, which was the pressure, the experimental pressure, minus, and then the Antoine equation is the a minus b over t plus c, all of that squared. Oh, this is outside. Okay. Cool. So now we can define our variables for nonlinear regression. Just call it like that. And we can use the vector and separate it. Using the minimize, we want to minimize the error and so now we can just make general guesses for what we think the values for those parameters will be. Right now, I'm just gonna guess, I don't know, 10 and 0. I don't know. See if that works. Okay, I think I figured it out. I think I had the parentheses wrong. Let's try just that. Yes. Okay, awesome. Now we can separate it. I was trying to do too many things at once. Alright, let's call our nonlinear parameters just A nonlinear, B nonlinear, C nonlinear. Awesome. And then we want to do the minimize. The sum squared error. And let's just make general guesses for what we think. Good guesses for what we think these values might be around. I'm just going to say 10, 10, and 0. I don't know. What happened? Okay, I think I figured out what I did wrong. I need parentheses here, I think. And the dot x. And the error is saying t. Oh, I think I made it lowercase. Let's try that. T. What if I did a restart and run all? Yay! Okay, awesome, that works. So now we have our parameters. Just gonna get rid of that space. Next is we're just gonna put this on our plot. So let's do another fig dot add scatter. And the x is our temperature. Y is the pressure. Or no, sorry, the y, we would use the parameters in the Antoine equation for the pressure to calculate the pressure. So the Antoine equation is the A minus B of that divided by T plus C. Okay, that was sweet. So then we're going to do the mode, and this one we're going to do lines. And for the name, we'll just say, I think I need an equal sign there. Let's do Antoine, and this is the non-linear. Okay, let's see if that works. Oh, O, B, N, L. Okay, huh. Well, it graphed it. So it looks like it works, but it's possible that we made a mistake or that our initial guesses for the parameters are just way too far off. So I'm going to keep going since we know how to find the specific values for the linear equation for the parameters, and then maybe it'll fit the data better. But if it doesn't work, then it could also be because I made a mistake somewhere. So let's just keep going and see what happens. We want to have, once we have our model, we want to be able to have a line with data that's not just, we want to be able to have points where we, even if we don't have data, we can still see, like, compare the temperature to the pressure. So we want to have like more plots on evenly spaced on our model, not just for points that we have data for. That way you can analyze it and interpret what the pressure will be given any temperature, not just ones we have points for. So we're going to put on the temperature equals and space, and let's just do, I don't know, 100 points. Okay, make sure I did the syntax right. Okay, awesome. So that'll be for later. All right, so now we want to make our design matrix, which we will be able to then get coefficients for the vector of unknowns and model the data in terms of linear regression. So let's set that up. Let's just call this X, because that's what I use it for on the board. And we're going to np.c underscore, and if you remember, we had the temperature in the first column, negative of the log of the pressure, and then the last column was all ones. And we want it to be, we want as many ones as data points, so like T. Okay. Let's make sure that works. T, why do I keep doing capital T? Maybe I should have just made it capital T. Okay, sweet. Now let's define our variables for the vector of unknowns. Let's just do linear regression. And we used, instead of A, B, and C, we used A, C, and D because we had B equals the A times C minus D, which was from when we moved the Antoine equation around, which I will show in just a minute. And we're going to do linear algebra. And we're going to do the inverse of the transpose multiplied by the design matrix. So this is this lin alg inverse is how we do the inverse of a matrix. The matrix transpose is just x dot t, and that symbol is how we do multiplication. Okay, so then x, and then we're going to multiply it by, oops, sorry, x multiplied by the temperature times pressure. Okay, let's see if that worked. Nice. All right, getting close. And we want to separate, we want to get the b value back, so we're just going to use what it was from before. Cool. Because that was just a string of constants, so instead of having all of the constants out like that, we just made it a different constant. Okay, so now let's see if it'll give us look at that. So now we have our values for A, C, and B that we can put into our model to get accurate coefficients for the parameters. Huh, that's amazing. Okay, glad that worked. So now all we have to do is graph it and we'll be done. If it works, if I did everything correctly. We're doing another on scatter plot. X equals, we're going to do the t-plot from up above where we had extra points. Y equals, then we're going to use our linear regression values that we just solved for. Minus b temperature plus and the mode, we're going to do lines again, and name, let's call this Antoine linear regression. Okay, see if that works. What did I do here? Let's try that. Of syntax. Oh, I think I need equal signs here. Okay, so I think I finally figured out my issue. I had the parentheses messed up over here, so it was only dividing by the temperature instead of the temperature plus the constant. So I think I fixed it now, but we can restart it and run the whole thing to see if it works. Oh, no, that's not what I wanted. Restart and run all. There's our data. Yay! Okay, so this model looks good. Alright, and then it plotted our linear regression model with the experimental data. And then here are the initial guesses for the parameters that we could ultimately put in here. So it would be 10, what was it, 10, C, so B is the last one, which is the 1700. And negative 34. And then let's do the restart. Run all one more time. Okay, so it doesn't look that different, but now we know it's as accurate as it can be. Okay, so now we have successfully plotted our two models. They are slightly different, but on top of the experimental data, so you could predict the pressure of the vapor pressure given any temperature for water. So even though they are slightly different because they were the linear regression and the nonlinear regression were calculated by various means, they are still pretty close to each other in terms of accuracy to our experimental data. But yeah, that basically finishes the problem. Thanks for watching. This was an overview of how to plot and model linear regression and nonlinear regression, and we used the Antoine equation for water vapor pressure compared to temperature.